So effectively, what is a program? Well, a program is an ordered set of functions designed to perform a specific task. This program is written according to a set of defined rules so that it can be translated to the binary codes that a computer understands. So effectively, a program is similar to a recipe that you might use in order to make a cake. That recipe follows a predefined set of rules, so that way anyone who wants to make a cake can clearly understand what it is that they have to do. So generally when it comes to making a cake, there is a list of resource requirements, such as the ingredients, how much of the ingredients are required, and then there is a set of steps to clearly illustrate how those ingredients are transformed from their raw state into that final product, which is the cake. So if you don't follow those sets of rules, then you're more likely to come out with something that's unedible in the end, or something that you won't be able to digest for a couple of weeks, or something that backs you up a bit. So therefore you've got to follow a predefined set of rules when you're making a cake. The same thing when you're writing a computer program. The computer program itself is that recipe that tells the computer or the processor the steps that it must go through in order to reach that desired result, or to perform the desired application that you require it to do. So the programming language itself is a set of instructions that can be used to construct a program. So once you know clearly what those steps are, you can then translate those individual steps into a program. But of course, before you can write the program, you have to clearly know and understand what the problem is. So generally, before you jump in there and start writing code, you need to sit back and think about what it is that you're trying to solve and how you can go about solving that problem. So if you spend more time in the thinking and solving stage, then the code will automatically write itself. So an algorithm is a step-by-step sequence of instructions that describes how to perform a particular task. In other words, it is a method used to solve a problem. Writing code is not the difficult part. It is writing the algorithm or solving that problem. If you can sit down and you can write an algorithm that clearly outlines the steps that must be performed in order to solve a particular problem, then writing the code is nothing more than translating those independent steps into program code. So if you spend a lot of time in the thinking stage, or the system analysis and design stage, then you would have broken the problem down to such basic steps that each step can be easily translated into code, and therefore the code is already written itself. So to give you an example of what an algorithm is, let's say you want to add two numbers together. That's a pretty simple thing to do, but if you had to explain it to a 4-year-old, it can be quite complex to them. So you'd break the problem down into intermediate, simple steps that a 4-year-old could follow. So you want to find the sum of two numbers. So first of all, you get the first number, you get the second number, you add the two numbers together, and you display the result. So they're the 4 steps involved in adding two numbers together. It's pretty straightforward. You've been doing that for years. But as I said, if you wanted a 4-year-old to do it, you'd have to clearly outline each step required. Same thing with a processor. It's just a dumb, inanimate object. It has no intelligence of any kind. You have to give its intelligence through that code that you write. So therefore you've got to clearly outline the steps required in order to do the most simplest of tasks. The saying, "There's more than one way to skin a cat," is ever so true when it comes to writing programs. There are always more than one way to perform a particular task or to perform a particular solution. So you can write an algorithm to solve a particular problem in many different ways. Okay, and of course the algorithm can be described in any language or symbolic code. So the whole idea of sitting down and thinking about the problem is to try and illustrate using some form, whether it's English language or symbolic code, to try and describe that problem, describe the solution, and then once you've described that solution in such great detail, then writing the code will effectively write itself. So the whole idea is to sit down and think clearly about the problem before you even so much as try and write any code. If you write code without thinking about the problem, what you'll end up with is a solution that doesn't meet the requirements, or you'll end up with a solution that doesn't work full stop, or you'll end up with a solution that barely works but is an absolute nightmare to modify down the track if you want to, say, improve it or make it a little bit more flexible. So if you can think about the problem, first of all, you can think about the limitations. So when you're thinking about the problem, the limitations of your solution will jump up and bite you in the nose. You can see clearly what the resource requirements are, and you can clearly nut out any sort of conceptual or fundamental problems that you might have at the system analysis and design stage. So that's the whole reason for doing a system analysis and design, because it's a lot easier to sort out problems when you're writing English statements or you're writing symbolic code, symbolic symbols. But then when it comes to writing code, there's a lot more difficult things you have to overcome, because if you obviously find out halfway through writing code, oh damn, I didn't take this into account, then it probably requires you to rewrite a fair chunk of that code. So it's always good to think about all these issues at the system analysis and design stage, and therefore when you write the code, it won't be a real problem. It'll be pretty much right itself. So like I said, we want to be able to, during the system analysis and design stage, or the thinking or the algorithm design stage, we want to be able to describe our solution using some sort of logical means and using a predefined standard. So therefore, when we describe our solution, we can show it to someone else and they can have an idea of what our solution is, because we're using predefined, a standard, so to speak, of a sort of way of representing our solution. So one of the ways that you can represent your solution is using flowcharts. Flowcharts are a great pictorial representation of a problem. They clearly show the flow of the program, and from my point of view, I quite like flowcharts because you can just look at the flowchart and see exactly what's happening. You can see the program flow, you can see, the data being moved around. It's quite a very simple means of describing a solution, but of course it's also a very illustrative way of describing it. Don't have to worry about people's incorrect spelling or grammar when they're doing flowcharts. So flowcharts uses a series of different blocks to represent different actions that we might be doing inside our solution. So the first block I'm going to talk about is the input-output block. And this is a generalized input-output block, which is used for when we want to read data from the outside world, or we want to write data back to the outside world. So any sort of flow of information that comes in and out of the actual processor. So this may be information moving to, a analog to digital converter, or coming from a general purpose I/O port, or coming from the serial port. So using getchar, or when we're writing data back to the serial port. So we can do like a putchar. These are the blocks that we might use for input and output. The process block is another block where we simply put the blocks to describe a particular action that we're doing. So when it comes to flowcharts, and I should have mentioned this on the previous slide, but when it comes to flowcharts, we actually write inside the block what it is that we're doing. So as far as the input-output was concerned, we may put right inside that parallelogram, A equals, some value from some input-output register of some kind. So we might clearly state that this is a input-output register and assign a variable, a particular value from a register inside that parallelogram. When it comes to the process block, of course, this is where we're doing the actual data manipulation inside our flowchart. So this is where you might put things like, A equals B plus C, or A plus plus, or A equals A plus 1, or something to clearly state, some sort of action that we're doing inside our flowcharts. We try not to put big English sentences in there, because if you've got to describe something with a big long English sentence, then obviously means that you need to think about that a bit more and break it down to more fundamental steps. So the whole idea of doing this flowchart in the first place is to try and get your solution broken down to such fundamental steps that the code pretty much writes itself. So you can pretty much read the flowchart and even execute the flowchart in your head and see exactly that it's going to work, and then translate that line for line effectively into your programming language of choice. Because it's a flowchart, we have flow. So we have a movement of, the program and data through the blocks to the end of our solution. So we have flow lines that clearly show the direction that we move from one block to the next. And of course the flow lines have arrowheads on there to show the direction. So it's very important that you have the arrowheads, so that way people can read your flowchart and see the flow from start to end. So when it comes to, say, doing an input-output block or doing a process block, you may want to describe some additional information that you couldn't squeeze into that block, or you might want to give some additional information that isn't 100% important to understand what that particular block's doing, but it may be additional information like additional assumptions or additional information that you might require when it actually comes to coding that particular block that you're doing. So you may have had a, say, variable A equals B plus C, and then you might want to clearly state in an annotation symbol that is a variable A, not the accumulator A, or something like that. Just things that make it a little bit clearer that when you actually do get to the coding stage, you've already overcome and already thought about some of the implementation issues that might crop up when you go to write the code. So an annotation symbol, simply a call out. The call out box points to the block in question, and then you put your additional information inside it. This is where you can put your English written statements that you might need to use to clearly describe something that might be a little bit vague inside a process or input-output or decision block for that matter. So when it comes to flowcharts, or flowcharts are solutions to problems, and like programs, our solution will not be sequential. It will not go from start to end in a nice little line of process or input-output blocks. There'll be chunks or sections of our solution where there'll be particular conditions that we're looking for, and based on a particular condition, we may cause our flowchart to split down to independent paths depending on the result of that condition. So when it comes to our decision blocks, these are little diamonds in which we write the actual condition that we're looking for inside the diamond, and therefore the result of that condition can either be a binary result, so it's either true or false. Therefore, out of each diamond, there'll be one input flow line into the diamond that gets us there in the first place, and then out of the diamond there will generally be two flow lines out of the diamond. One for the true condition, if that condition is actually met, and one for the false, if that condition is not met. And because we don't know which line is which, we generally write on the line a label that clearly tells us which flow line is the true flow line and which flow line is the false flow line. That way, when you look at the flowchart, you can clearly see, okay, if that condition is met, then we go down this path to these process or input-output blocks. Preparation symbol. These are generally symbols that don't really play a role in our solution, but they are actually required for implementation means. So it might be where we might set up, say, a stack pointer, or we might set up the, turn the interrupts on, or we might set up a loop counter, initialize it to some value. These are the things that don't generally play a role in our solution, but they are required when it comes to implementation. We need to be able to have these thought out in the system analysis and design stage, so therefore when we get to the implementation, we've already nutted out all the difficult bits. So the preparation symbols generally used for our housekeeping, so to speak. A predefined process. This is where the ultimate goal of system analysis and design, or actually algorithm design, is to take a big problem and split it up into a series of smaller problems. We don't really want to try and deal with our problem in one big hit, because one big complicated problem is a lot more difficult to solve than a series of smaller, simpler problems. So we try effectively to split our big problem into smaller problems. So what we like to do in our top level flowchart is we like to have the start and the end of our flowchart, and then have a series of predefined processes inside that flowchart. So these predefined processes effectively placeholders for other flowcharts. So we may have a complex algorithm that we need to, so you might have a really complex algorithm that can be split up into 4 simpler algorithms, and therefore in our top flowchart we'll simply have 4 predefined tasks that are placeholders for those various steps that have been split up into smaller, easy to understand chunks. So we'll have predefined processes in our top level flowchart, and then those predefined processes effectively say, hey, the flowchart that implements this chunk of the solution is actually described in a bit more detail somewhere else. So therefore you can actually go to another flowchart, and therefore that flowchart will illustrate the steps involved in order to implement that predefined task. So the predefined tasks are placeholders, and therefore you can go somewhere else in your flowcharts and see that actual independent flowchart of that predefined process. So it's a means of actually being able to segment that complex problem into smaller, easier, bite-sized sort of chunks of code. Terminal blocks are very important when it comes to flowcharts because we'd like to know where our flowchart starts and of course where our flowchart ends. So when it comes to a program generally starts in a predefined place and it usually ends in the same place. So therefore our flowcharts will always have a start or a begin block and an end block. So therefore we can clearly see where the flowchart starts by having a terminal block that has start in it or begin, and we can clearly see where our flowchart ends because there will be a block, terminal block with the word end in it. So we can see the flow from the start to the end via the input, output, process or decision blocks that we have, or preparation symbols or predefined task symbol blocks that we have in our flowchart. The other thing is when we have predefined task blocks to say, hey, this chunk, this part of the solution is described somewhere else in a separate flowchart, generally when you go to that flowchart of that predefined task, the starting terminal block for that predefined task will in fact not have start or begin in it, but will in fact have the name of the particular predefined task. So therefore you don't have to go looking for which predefined task it is, you simply look for the flowchart where the starting terminal block actually has the name of that predefined task. And then of course in our predefined task it simply goes through the various other blocks, the input, output, process, predefined if you've got more predefined tasks, decision blocks and so forth, and it will end at a end terminal block like a standard flowchart. Of course, when you're doing flowcharts and you've got all these flow lines buzzing around all over the place, it might be easier just simply to remove the flow lines, group them together in one point, and then maybe put a connection symbol there instead. So put a little circle there. So you have all these arrows going into a little circle. You put a label inside the little circle, say like P1, and then somewhere else in the flowchart you have the same label, say P1, and you have flow lines coming out of it, and therefore it's assumed that there is a flow line that connects those two connector symbols together, but you don't have to draw it, it's just assumed because they've got the same label. You can make the assumption that they connect up. So it's a way of making your flowcharts a little bit easy to read instead of having flow lines buzzing around everywhere. Okay, when it comes to a program, effectively the anatomy of the program is extremely important and crucial to understand. If you can understand how what a program consists of, and then of course you can write adequate solutions that will be able to be turned into programs. So when it comes to programs, flow of control refers effectively to the order in which statements are executed. Every program has common flow structures. It doesn't matter which programming language you're using, they will have program flow structures. They may have a limited number or they may have a whole heap, but they generally have some means of doing flow of control or common flow structures. So the control statement is of course the lowest fundamental unit of a program. We make programs up by fusing these various control structures together. Each control structure has one entry point and one exit point. So there's always one point where we go into a control structure and there's always one point where we exit that control structure. So the basic control structures are sequence. So this is our single step where we simply go through the various steps one by one by one by one. So when you do a recipe for a cake, you simply go through step 1, then step 2, then step 3, then step 4, then step 5, then step 6. There's very rarely any change of flow in a recipe, so it's very sequential, one step after the other. When it comes to selection or conditional statements, this is where we get down to the code and we have to do some test of some kind to see whether in fact a particular condition has taken place. If it has, we go down one path. If it hasn't, we go down another path. So we can have selection control structures which is simply if then. So if it's true, we do this. If it's not true, we don't do anything. Or of course we've got the alternative where if a condition is true, we do this chunk of steps. If it's not true, then we do a separate chunk of steps, and then we meet up down the bottom at the same point. We've got iterative loops as well. So this is where we can do our, while a particular condition is true, we do a chunk of statements or a chunk of steps that we need to do. So when you're doing a recipe and you might be making biscuits, there might be a part of the recipe that says, grab a handful of dough, mash it up, flatten it down to make a biscuit. Repeat this until the dough is being used up. So therefore it's got a condition there that while the dough hasn't been used up, we keep patting down the dough, putting it into the biscuit tray to make the biscuits. So we can do that with a repeat until. So we can do the same thing, but we might need to just phrase slightly different. So repeat patting the biscuits and getting the handfuls of dough and patting them down in the tray until the dough has run out. So it's the same sort of thing, but there is a slight difference between the two, and I'll get to that a bit later on. And then we've got the for iterative loop as well. So this is where we know beforehand how many times we're going to do it. So we don't necessarily need to know beforehand at compile time, but based on some sort of variable of some kind, we can do a predefined set of tasks a certain number of times. Okay, so we're not looking for a condition anymore. We already know how many times we're going to be doing it, and we're going to be doing it that many number of times. So we can use control structures in combination with one another, and this is where we call it nesting. So we might have a if statement inside a for loop, or a while statement around a for loop and things like that. So you can actually join them all together to make nested control structures. So when it comes to sequence, as I said before, this is the simplest control structure. This is simply where we do one step after another, like in the recipe. Step 1, step 2, step 3, step 4, step 5, step 6, and so forth. So they simply do these statements in our program in the order that they appear. Okay? And of course, the normal flow of a program, of course, is sequential unless the program is directed otherwise. So unless we hit one of the other control structures, the flow of the program is always sequential. So even when you're inside a iterative control structure like a for loop, you're doing those statements sequentially inside that for loop. And then when you get to the end of the for loop, you go back up, and then you might change that variable, the counter variable that you're dealing with, and then do those set of statements sequentially once more. So to give you an example of a flowchart, we've got a set of sequential statements. We've got our terminal block at the top with the word start in it, so that clearly says, hey, this is where we're starting our flowchart, at this block here. Then we've got a equals 3 plus 2. Okay, so therefore that's simply a process block that simply puts the value of 3 plus 2 into the variable called a, so that means a will have the value of 5. Then we go on print a, so we've got an input-output block to show that we're printing the value of a, and then we've got a terminal block, which is the end block. So you can clearly see that that's sequential. We've got a sequence of flow from the start to the end. There's no branching out or anything. There's no decision blocks. It's simply sequential from one to the next to the next. So when it comes to selectional control structures, this is where we have our if-then-else structure. So simply we have a particular condition that we're testing. So if that condition is true, then there's a chunk of statements that we actually implement. If it's not true, then we simply skip that set of instructions that we want to do. So if the condition is false, then no task is performed and the structure is exited. So you've got to notice here in this little segment of a flowchart I've got on the right that if the statement is true, we do the then chunk of blocks. And you'll see that once we're finished with the then, we then join up at the same location as the false. So we join up, and there's only one entry point into this flowchart segment, and there's only one exit point out of this flowchart segment. So that's very important to keep in mind. There's one entry, one exit out of all these control structures. So to give you an example of this, we have start a equals 3 plus 2. If a is greater than 5, then we print a is greater than 5. So we'll clearly see that we've got our decision block with a condition inside the decision block, and we've got a true line to show us what happens if that condition is true, and we've got a false line to show what happens if that condition is false. So you can actually see exactly what's going to happen if you were to write this flowchart into code and actually execute it. You can see that A is actually equal to 5, so therefore that condition is actually false, so therefore nothing will appear on the screen. So the true part of our code will never in fact actually run. Okay, so it will never actually print A is greater than 5 to the screen. So that's how we can do our if-then selection or conditional flowchart. So when it comes to situations where we have, we have a condition and we have a true chunk and a false chunk of code that we actually want to run, how can we go about doing this? So you can see that we've got our diamond again for our decision block. We have a true line that then points to the then chunk of process blocks. So the then chunk of process blocks are the blocks that we're going to do if in fact that condition is true. We have also out of our if, we have our false chunk of blocks. So if that condition is false, we have a series of process or input-output blocks that we might implement. And then you can see that after we do the then and after we do the else, we both meet up at that same point again. So there is one entry point into this structure, and there is one exit point out of the structure as well. So as I said before, with the decision block, we have one entry into the decision block, and we have two exits out of the decision block. So we have a true and a false line. It's very important that you label those lines, because when someone reads your flowchart, if you haven't labeled them, they'll have no idea which flow line you're going down if that condition is true or false. So it's very important that you actually clearly label the flow lines out of a decision block. So to give you an example, we have start A equals 3 plus 2 again. We have that decision block to do that same condition again. A is greater than 5. So if that condition is in fact true, we then print A is greater than 5. If the condition is false, we print A is less than or equal to 5, and we both meet up at the same point just before we end. So there's one entry point into that control structure, and there's one exit point out of that control structure. So by looking at this flowchart, you can clearly see what's going to happen. It's simply going to print A is less than or equal to 5 to the screen. So these are very simple problems, but it's clearly showing exactly what's happening by doing this flowchart. So when you're doing your slightly more complex problems, you want to generate the flowcharts, and therefore the flowcharts will clearly show the solution and how you need to actually implement it. So another nested sort of selectional block that you can have is, of course, the case statement, and this is simply where you have a series of conditional statements nested one after another. So you simply do an if condition. If it's true, you do this. Otherwise, you do a false chunk, or you can simply go down to the next check. So if you're doing like a case statement that you might have in high-level languages such as C or Java, you can see that you simply do a check on a particular variable, and you compare that with different values, that one variable with different possible values. So we can simply have a series of decision blocks, one after another. So if one condition is not true, we simply jump down to the next decision block, test another condition. If it's not true, we jump down to the next decision block. So you've got a series of decision blocks on the false flow lines of those previous decision blocks. And therefore you can clearly get it to check various different values to see if it's a particular value, so to speak. And then, of course, once a particular condition is true, it simply doesn't worry about going to the other decision blocks. It simply goes to the true chunk of statements or the then chunk of statements, and then it all meets up down the very bottom. So you can see that even though this has got two decision blocks in it, we have one entry point to the top decision block, and we have one exit point, which is after the last false chunk of statements out of the last decision block. So we have one entry point, one exit point. So to show you an example of this flowchart, so using the same sort of example as before, we've got A equals 3 plus 2, then we've got A is greater than 5. If it's true, we simply print A is greater than 5, and then we end up at the end terminal block. However, if that's false, which in fact it is, we go down to the next decision block, and that does a check as A is less than 5. If A was in fact less than 5, which it isn't, but if it was less than 5, it would go down the true line and hit print A is less than 5, so to print A is less than 5 to the screen. But we know it's not less than 5, it's actually equal to 5. So therefore, because it didn't trigger the A is greater than 5 block, it's gone down the false path there and hit the A is less than 5 block. Because it hasn't triggered that block, then it's simply gone down that false path, and of course if A is not greater than 5 and A is not less than 5, then of course it implies that A is equal to 5, so therefore it gets to the input-output block there that prints A equals 5 to the screen, and therefore it ends at the terminal block, end terminal block. So you can see that all those, inside here we've got 3 possible paths that it could have gone down. It could have gone down the A is greater than 5 path, A is less than 5 path, or the one like it did, the A is equal to 5 path. So all those 3 paths all terminate at the end terminal block. So they all join up together just before the end terminal block. So that's what you've got to make sure, that your decision blocks have one entry point and one exit point. Okay, so when it comes to iterative structures, we also name them, call them loops. These are used where the same program steps must be repeated many, many times. So it's either repeated a set number of times in the case of a for loop, or it's repeated as long as a particular condition is true, as far as the while, do, or repeat until iterative blocks are concerned. So this always involves testing a particular condition in order to leave the loop. So whether it's a while, do, repeat until, or a for loop, we're always checking some particular condition to see if in fact we're going to leave that loop. So in the case of a for loop, we're checking to see that our counter variable is still less than or equal to our particular termination value that we've given it, or to make sure that it's actually still equal to that particular condition that we have set for our for loop. So when it comes to iteration, our while do structures, these are basically where we test a particular condition, and as long as that particular condition is true, we do a predefined set of instructions. So if the condition is true, we simply do those instructions, we come back and we test that condition again. And we keep doing that loop as long as that particular condition is true. If the condition is false, then we simply break out of that loop and we don't keep looping, we simply continue down the false path. So as long as the condition is true, we keep doing the do and repeating, come back, check the condition, do the do instructions, come back, check the condition, do the do instructions. Second that condition is false, we simply continue down the false path, which means we're broken out of that loop. So like before, there is one entry point into this control structure and there's one exit point out of this control structure. So to give you an example of this, I've used an example with the getChar subroutine. So because that's a serial subroutine, I've also included the predefined task of init SCI as well. So simply we start, we initialize the serial port, we then simply do our condition, we check that if B is not equal to A. If it's not equal to A, then we simply do a getChar, which will grab a value from our serial port and it will return it in B. So you can see in this predefined task, we've got 2 predefined tasks here. Init SCI, I've got in, and I've got a colon, and then I've got nothing. So there are no inputs. Same thing with the out, it's out and colon, so there are no outputs. So the init SCI has no inputs, has no outputs. There are no arguments whatsoever for the init SCI routine. However, when it comes to getChar, this predefined task has no inputs. Okay, so therefore in colon is null, is blank, but it has one output. So we have out colon B. So therefore it clearly defines that the output of getChar will be in variable B, or in this case it's really accumulator B, but variable B, we don't want to think too much about how we're physically going to implement it right now. We can call it B, and therefore how we implement that when we write our code is up to us. But right now it's coming back in variable B, and you can see that as long as B is not equal to A, we're stuck in that loop. So if someone was to push A on the keyboard and getChar was to return the value of character A, then we would simply break out of that loop. So I've said character A and I've defined it as a character A because it's in single quotes. So the second we get back the character A, we simply end that flowchart. So something to keep in mind here with the while do, we checked the condition, then we do the instructions. Okay, so it requires a pre-conditional check before we actually do anything. Okay, it's something to keep in mind that we actually do the check, then we do the instructions, because that particular check resulted in a true value. When it comes with a repeat until, effectively it changes slightly. With the repeat until, we actually have the set of instructions we want to do first, and then we check the condition. So with the repeat until, we actually guaranteed to do those sets of instructions at least once. That's how the while do differs from repeat until, is the fact that a while do will check the condition first. If the condition is true, then it will do the instructions. With the repeat until, it will do the instructions that you want it to do first, and then check that condition. If that condition is true, then it will go back and do those instructions again. So with a repeat until, you're guaranteed that those instructions will run at least once, when with a while do sort of structure, you have no guarantee that those instructions will run at all, because if that condition is instantly false, then the instructions will never run with a while do. So it depends whether you want to do a pre-check or a post-check to which control structure you actually do. So you can see with the flowchart on the right, we have our repeat instructions, then we have our until condition, and we simply change the logic around to be the opposite of what we actually condition we're looking for, and therefore if it's false, because when that particular condition is true, because normally with a repeat until, it's when that condition is true, then we want to stop. So therefore we have the false path going back to the repeat. Okay, and then the true path is actually the path that exits. So you can see, like before, one entry flow line, one exit flow line. So to give you an example, same sort of example we had before, we simply we start our code, we do init SCI, okay, and we initialize it, so there's no arguments for our init SCI. We then do a get char, so we have our out B, so we simply have our output coming back through B, and then we check the value of B to see if it's A. If it's not A, we go back and we do our get char again. If in fact the value of B is in fact A, then we simply exit our flowchart back to the end block. So when it comes to our iterative for structures, then effectively an iterative for structure is nothing more than basically a repeat until block, except that we simply initialize a counter of some kind. So we have a start block, which is usually initializing our counter. We have a body of our counter, which is the chunk of statements we actually want to do a predefined number of times, and we have our end condition of our flowchart as well. Okay, so therefore there's generally three sections of our for structure. And of course, as part of our body, we actually want to ensure that we increment our counter in some way, or decrement it, or do something with it, depending on what the application defines, because eventually we're going to want to exit this structure. So therefore the for structure initializes the counter to the starting value. We have the counter is compared to the ending value, and simply if the counter is greater than that ending value, then the for structure is exited. If it's not, then we continually repeat inside that body, keep running those instructions over and over and over and over again. So at the end of the body, as I said before, we need to ensure that our counter is incremented by the step size that we've defined, so whether it's incremented by 1, incremented by 2, or whatever, but then we need to increment it, and then we go back up and we test, we then increment it at the end of the body, then we test that condition in the end. If in fact it's still less than the end value, then we go back up to the body, or if in fact that condition we're checking for is still true, then we simply go back up to the body and keep running again, then increment that particular counter as part of that body yet again. So to give you an example, we simply have our start. So this is we have the variable A, which is our counter. We initialize the variable A to be 0, and we simply print the value of A to the screen, and then we go A equals A plus 1. Then we then check to see if A is less than or equal to 5. If it is, then we go back up to print A. So if we print the new value of A to the screen, we then increment it again, and we do a check to see if it's less than 5. And then if in fact it isn't less than or equal to 5, so in fact the value of A is 6, then of course we end. So what will happen when you run this flowchart, you actually get the values of 0, 1, 2, 3, 4, and 5 printed to the screen. So you can see that the way that the for loop actually works in an iterative sort of way by looking at the flowchart. We can also do our loops in the other order, so we can actually have A equals 5, then we can print A, and we can do A equals A minus minus 1, so we can actually have our for loops go backwards. Depends on your application to which way you do. If you want the, if you're printing the numbers to the screen, you want them to go 0, 1, 2, 3, 4, 5, you do it the previous way. If you want them to go 5, 4, 3, 2, 1, 0, then you do it this way. So it depends on your application to which way you get your loop counters to actually work. So we start at 5, we print A, and then we go A equals A minus 1. We check the condition. If the condition is still true, we go back and we keep printing. So we keep staying in that loop until the value of A is in fact -1. The second A is -1, then we end that flowchart. So you can see that the flowchart would in fact result in the values of 5, 4, 3, 2, 1, 0 being printed to the screen. So which type of loop do you need to use effectively? So we've got 3 different possible iterative structures. Which one do you use? Well, it depends on how much information you know and what sort of process you need to go about to get that information. So do you know beforehand the number of iterations that it needs to do, or is there a variable that holds the value of the number of iterations that it needs to do? If yes, then obviously you need to use a for loop. If you don't know beforehand the number of iterations, but you know that it depends on some sort of condition, then of course you need to use a while do or a repeat until. So which one of those 2 structures you use will depend on, do you need those instructions to run at least once first to maybe generate the value that you're going to compare against, or do you need to check before doing the chunk of instructions? So do you need to pre-check or post-check? That will define whether in fact you're using a while do or repeat until, whether in fact you need to check it first or check it after you've at least done it once. So that will basically define which sort of control structure you need to know based on what sort of information you have and whether in fact you want to run those instructions once or not beforehand. Okay, so some examples, you might have a while the X key has not been pressed, do something. So you may, that sort of defines a while condition of some kind, and then you can restructure that exactly same thing as a repeat until. So you can repeat a chunk of code until the X key is pressed. So it depends on how you really want to word the problem to which way you actually implement it. So variables, when it comes to variables, it's always good to think about the variables when you're doing your system analysis and design, because then that will impact on your resource requirements for your solution, as well as makes it very clear on how your data is going to move around inside your flowchart. So if you've got a very good idea of the data you're using when you're doing system analysis and design, it'll make it a lot easier to actually code your solution. So variables, of course, are where the program or algorithm stores its data. And of course, these variables are located in the memory of the computer, in the RAM section of the computer, and the size of the variable depends on the type of data that you're going to put inside that variable. So it's a good idea to know your data sizes. So if you know you've got an array of 10 or 20 elements, it's good to make a note of that. So when you're assigning a value into this particular data, you might want to put an annotation symbol to actually clearly state, this is an array of so many bytes and so forth. So therefore, when you implement it, you can allocate the right amount of space for that particular variable. We give variables a unique name and generally try to give them names that are descriptive. So we try not to use the variable name A or B or C or D. We try to use variable names that clearly state what it is that we're storing inside them. And that way, when you read your code is very readable. Or when you even read the flowchart is very readable. It's very clear what you're sticking, what the right-hand side of an equation is doing, because it's going into a variable on the left-hand side that clearly states what it is, what's happening. So try to give them descriptive names. That sort of makes it a lot readable and makes it easier for someone to read your flowchart or read your code. And of course, variable names that you've given in your flowchart, they have to propagate into your code. So therefore, when you look at your flowchart and you look at your code, there's a clear link and connection between the two. So variables, of course, can be used to store numbers, letters, strings, or arrays. Okay, and of course, strings are nothing more than groups of letters that we might chunk together in an array. It's basically an array of characters. Strings are normally shown between single quotation marks. Going to give you some example here: hello world, coffee time, and so forth. So they're examples of how you might define a string in a flowchart and also inside a program. But as I said before, when it comes to doing this whole system analysis and design, the whole idea is to try and split that task up into a series of independent or modular chunks of simpler tasks. So we try to design this program so it can be easily developed and it can be easy to correct and of course easy to modify. So we try to split the big problem up into a series of smaller independent chunks. So the best method of programming is to break up a program into smaller tasks called modules, okay, and this is known as modular programming. So we try to make the complex problem a series of smaller, more manageable, bite-sized chunks of the problem. So therefore each module can be considered as a separate sub-program, and therefore you can implement and develop those sub-programs independently and prove that they work, and therefore then integrate them back later on. So you try and make that bigger problem to a series of smaller, more manageable problems. So each module must do what is required of a small program. It should receive data, process the data, and produce a result of some kind. Okay, larger modules should always be broken up to smaller modules. If you're trying to deal with the problem and it's still too complex, then it's obvious that it needs to be split up into smaller, more manageable chunks. So therefore, you would split that up into a series of intermediate steps, and therefore take those intermediate steps to make sub-programs or modules or subroutines out of those various smaller chunks. It's always easier to develop the code for many small tasks than to develop the code for a large program made up of many tasks. So it's always easier to deal with smaller programs than it is to deal with a big program. So even though it might be a whole heap of little programs that might take you a little bit more time, it's actually a lot easier and a lot more less stress on the brain to do smaller problems than it is to do a real big giant one. Try to make sure that when you're doing a modular programming and you've got a subroutine, that it really doesn't occupy more than a screen full of text, because you really want to be able to see a subroutine on the screen at one time and clearly see by looking at it visually exactly what's happening inside that subroutine. So you don't really want to be going up and down, pages and pages of code. You'd like to be able to see it all on one screen at the same time. Each module should be able to be verified by itself. That's the whole point of doing this modular programming, is that you've written a small subroutine, then you write some test code to test that subroutine. Therefore, you can prove that the subroutine or the small subprogram actually works by writing it a test code of some kind. So therefore, if you know the subroutine or the subprogram actually works, then for later on when you integrate it into the big problem, you know it's not going to introduce any issues. So you try to not only make them into smaller, manageable chunks of code that you can write, you can then also break them into smaller, manageable chunks of code that you can then test independently, ensure they work, and then when you bring them all back together at the end, you know that the final solution isn't going to be an absolute mess. So the whole idea of making that smaller program that you can test is the fact that it's easier to find a bug in 10 or 20 lines of code than it is to, say, find a bug in 500 or 1,000 lines of code. So try and make it smaller, and therefore your scope of search when it comes to looking for a bug is limited to only one little subroutine or subprogram. And then because each of those little subprograms or modules have actually been, or subroutines have been tested independently, and you know they all work, therefore when you bring them all together into the big main program, you know that if all of a sudden it doesn't work, it's only because of the way that two subroutines might interact with one another. So you know the subroutines themselves work, but maybe the way the variables you're using to pass data around are different between the two subroutines. So therefore you might go, oh damn, I've got the wrong one. Then you might rip that subroutine back out, change it with a new variable, test to make sure it still works, and then bring it back and integrate it again, and know that because now you've fixed up that way that they communicate, they're going to integrate properly and they talk. So try and bring them back together one at a time. So you generally join two subroutines back into the main program one at a time, test them, they work, then bring another one in, and therefore if when you bring the third one in, things don't work, you know it's something to do with that last subroutine that you brought in. So therefore your scope of searching for a bug is in fact limited. So doing a modular programming is very beneficial when it comes to writing the code as well as debugging the code. So it's crucial that you should do a modular programming sort of method of writing your flowcharts as well as implementing your code. So if you've pretty much enforced a modular programming sort of mindset when you wrote your flowcharts, therefore you'll have a whole heap of predefined tasks, and therefore your code when you write it will also follow that modular sort of format that you've done in your flowcharts, and therefore it'll be easy to write, easy to integrate back, and you'll basically get from original problem to solution a lot quicker if you do a modular programming sort of method of implementation. And of course, because you've done a modular programming method of implementation, your code is actually easier to upgrade and modify down the track, because then you're only modifying a little subroutine, or you may in fact just remove a subroutine and insert a different one. So doing a modular programming makes your code a lot easier to maintain as well. When it comes to our programming that we're going to do, we refer to subroutines as modules. That's why I've interchanged that word so far. I've used the word modules and subprograms and subroutines all to refer to the same smaller chunk of code that we're actually doing. Subroutines are called to perform a specific task by the main module or other modules. So subroutines are in fact our equivalent of a predefined task. So you've got in your flowcharts these predefined tasks. When you write them in code, they'll become subroutines. Subroutine can have values passed to it. These values are called arguments. So when it comes to passing arguments into our subroutines, we've got two main methods that we can pass the data to the subroutine. One is we can pass data via the various registers of the processor, or we can pass data via the stack. Generally, it's easy to pass data via the registers of the processor. So generally, you'll load up a register in the processor with a particular value, then you will simply jump to that subroutine. Okay, so for example, I've got the example here of putchar. Putchar takes whatever character you've put into accumulator B and prints that to the terminal screen. So therefore, we simply load accumulator B with the character B, and then we simply jump to the subroutine putchar, and therefore it will actually write the character B onto the screen. But we'll talk a bit more about, you know, the mnemonics and the operands and things like that in the subsequent lectures, in topic 3 lectures. So effectively, how subroutines are executed. So each program line is executed sequentially until the line that jumps to the subroutine is reached. So when we get to that line that says JSR to putchar, in the previous example, then the processor simply jumps to that subroutine. Execution starts at the first line of that subroutine, and therefore we simply go through that subroutine block by block by block until we get to the end of that subroutine. Then when we get to the end of that subroutine, we simply jump back to the line after where we called that subroutine, okay, or where we did the JSR to the subroutine. So therefore it simply runs in the main program, hits that JSR, jumps off the subroutine, runs through that entirely until it gets to the end of that subroutine, and then jumps back to the instruction after the jump to subroutine that we had to jump to that subroutine in the first place. So therefore we'll go back and then continually running sequentially in that main chunk of code. So to give you an example, we're simply in the top level, like in our main, we're simply doing something. We jump to subroutine sub 1, so therefore we then jump down to subroutine 1, we do something, and when we finish that, we go back up and we go to the line after the jump to subroutine, and we continue doing something on our main. So therefore you can sort of think that subroutine could be inserted into that jump to subroutine section of our main, because that's effectively what the program's doing. It's simply jumping somewhere else in memory, running that subroutine, and then coming back to the instruction after where we actually ran that, back to the instruction after when we did the jump to the subroutine. So to show you this a bit more illustratively, we simply, through an animation, we do something in the top level, we jump to the subroutine. So we go down to the subroutine, we do something in the subroutine, we do something again, and when we get to the bottom of that subroutine, we then simply jump back to the next line and start executing that. So that's to show you, both in descriptive words as well as an animation, exactly what's happening when we run our subroutines. So how do we get to the stage of a modular program? Well, effectively, this requires us to do some top-down design. So top-down designs, we start with the major overall big problem, and we try to segment that into smaller more manageable bite-sized chunks. So we do a process of refinement. We take a big problem, we split it up into a series of independent programs. And then we take those independent programs, we split them up even further into even smaller independent sub-programs. And they, effectively, these little chunks we split up into will be our subroutines. So therefore, we simply name each of those blocks. They become our subroutines. And if you've taken a block and split it up into smaller blocks, then that subroutine will then call other subroutines to do those smaller blocks that you've then segmented it into. So your program will, in fact, clearly show whether, in fact, you've done a top-down design or not. So we simply take the big problem, split it up into smaller, very general blocks. We take those very general blocks and we split it up into even smaller blocks. So it's a process referred to as successive refinement. And we simply keep breaking down the blocks in the level above until the task is broken up into blocks small enough to be individual modules, or to a point that it's so basic now that we can very easily write the program or generate the flowchart for it. So to give you an example, I'll pick something that hopefully you're all very familiar with, and that is if you wanted to plan the party of the century. You know this is a big task. You know that for a party to be successful, there are key elements that the party requires. So you've taken the big party of the century and you split it up, first of all, into 3 key areas. So you've got your guests, you've got your venue, and you've got your entertainment. So party of the century needs guests, venue, and entertainment. So then I can take the guests and I can split that up even further, so I can see how many guests do I want to invite, who are they going to be, and why, what purpose am I inviting them for. Of course, when it came to the venue, I might want to think of location and size. So there may in fact be a sort of relationship between the guests and the venue. So there might be a very loosely coupled relationship there. And then, of course, entertainment. When it comes to entertainment, it might be music, alcohol, and food. So these are the other key things that might be considered under the entertainment category. And then, of course, you could subdivide music up into, what type of music. Am I going to require a DJ, so forth and things like that. So you can simply keep splitting up these problems into smaller, more manageable tasks until you've got a big list of things that need to be done. So you've got a big to-do list. So you split up into this thing that maybe at first seems so overwhelming and so difficult to actually do. You've then gone and split up into such simple tasks that you now just got simply a big long to-do list that you can simply go through each task one by one, and it's made that almost impossible party of the century into a very small, very long list of very simple tasks that anyone could actually do. So when it comes to doing a modular flowchart, as I said before, when you've done a top-down design and you've got a very modular sort of result happening, effectively what it's going to be in your flowcharts you'll generally end up with a flowchart with a lot of predefined tasks in it. So the predefined tasks will clearly state, hey, this is my modular bit that I'm going to describe in a bit more detail somewhere else. So when it comes to a modular flowchart, you simply start with the main thread. So you've got a start. You might have a variable, that you're assigning the value of 3 to. So we've got A equals 3, and then we've got a task A. So this is a task that we actually need to do. So obviously in a real modular flowchart, you'd have a lot more predefined tasks, because this seems a bit pointless just having one predefined task. So we've taken one big problem, we've split it down into one sub-problem, which doesn't seem like a very logical modular way of doing it. But generally you'd end up with one top flowchart with a series of predefined tasks in it, because you've taken that big problem and you split it up into a series of smaller sub-problems. So in this case, we've got task A, and we've got the variables, input variables and the output variables listed in brackets after that name of task A. We then go to the flowchart for that task A. So there's a predefined task called task A. We have a separate flowchart. Inside that, we have an input of I. We have the output of J. And inside that sub-predefined task flowchart, we have J equals I plus 1. So something to keep in mind here is the fact that when we call that predefined task, so in the predefined task block, we have in A. That A variable that's in our main flowchart, that A variable is in fact mapped to our I variable inside our predefined task. So therefore, in fact, I will be equal to A. Same thing when we get to the end of our predefined task and we've given a value to j. J is our output. So therefore, when we go back to the main flowchart on the left, in fact, the variable c will in fact have the variable that j had in that predefined task. So therefore, the value of j is passed back to our variable c. So therefore, the order and the location of the variables in that argument list is extremely important because they do a one-to-one mapping. Okay, so when you're using predefined tasks and you've got those subroutines or the predefined tasks described in a bit more detail somewhere else, you've got to ensure that they map one-to-one those variables. So some important techniques for developing flowcharts. We basically need to use a standardized flowcharting template. So we need to use it with clearly recognizable symbols, follow some ANSI recommendations for symbol use. So therefore, the flowchart that we actually develop, we can give to someone else and they can actually read it and understand it. We try not to crowd or clutter the flowchart. We ensure proper spacing between symbols. If in fact your flowchart's not going to fit on one page, then use some connection blocks and tell the reader that this chunk of the flowchart continues on the next page. Number the pages you flowchart sequentially. Okay, specifically the title of the program, the date, the author on each separate page. Especially if you've got connection blocks that go to a second page, you need to clearly state on that connection block which page it goes to. Okay, so not only does it have the label name that we're going to look for on that page, but also the page that we need to then go look at to find out where this continues. So some other important techniques for developing flowcharts is, of course, chart the main line of data flow and system or program first. So we always do our top-level flowchart, and then if that consists of a lot of predefined tasks, then we simply then have a wholly separate flowchart somewhere else. So we try to get a very basic flow of the program, so someone can just look at your top level and get a very basic idea of what the program is doing, and then if they want any further detail on what a particular part of that top flow actually does, then they can go to that predefined task and see it somewhere else and see that detail that they require. So we try to get a very basic overview flowchart to begin with, and then they can get that additional information by looking at the predefined tasks. Right within the symbols, avoid using too many words. If necessary, use the annotation symbol. So we try to leave as much words out of a block as we possibly can and try and squeeze all those words into an annotation symbol instead. So you try to make what it is inside a process or input-output block very clear and very concise exactly what's happening, and then maybe put a bit more description or a bit more illustration in an annotation symbol. Choose wording to suit the reader of the flowchart, so don't make it too complicated if the person reading it is not technical. Be legible, neatness counts, so nothing worse than having a big mess of flow lines going everywhere and it being very difficult to actually see where or what's actually happening in your flowchart. Of course, if the flowchart becomes complex, so a lot of flow lines running around, then of course use connector symbols to reduce the number of flow lines. So try and make it look very neat. Of course, the other things that are important when it comes to doing flowcharts is collect your incoming and outgoing flow lines so that the number of lines entering or leaving a symbol are minimized. Okay, and use a flowchart as a guide when you code your program. Okay, change it when necessary. So if you've gone and you've written your flowcharts and you've gone to implement those flowcharts and there's something you didn't realize and you've got an issue, it's no longer going to be like you did in the flowcharts, then simply go back to the flowchart and nut it out at the flowchart level. Don't worry if you've got to a point in your code and it's not going to work. Stop coding, go back to your flowcharts, nut it out at the flowchart level, update your flowcharts, and then go back and code again, because it's a lot easier to sort of conceptually try and nut out a problem in the flowchart domain than it is to try and nut it out when you're actually coding. So you may in fact end up doing 4 or 5 or 6 or 7 different iterations of your code if you try and deal with it in the coding domain before you actually get that solution, whereas when you go back to flowcharts, 6 or 7 different iterations of flowcharts is just simply rubbing out blocks, drawing new blocks, rubbing out new blocks, and so forth. It's a lot quicker than actually doing code. So of course, also cross-reference portion of your flowcharts to your source code. So therefore, when someone reads your flowchart and reads your code, there should be a direct one-to-one mapping. Okay, so use the same variable names, and the same program flow should be seen in the flowchart as it is in the code as well. Also, try and be consistent with the level of detail that you show in your flowchart. Do not chart every detail, but do not leave out important details. So therefore, when you get at the top level, try and make it a very overview. Then when you get down to your subsequent predefined tasks, then get down to the nitty-gritty details, to the point that you can simply then translate your flowcharts into mnemonics or program instructions. Always try and put yourself in the reader's position. So always try to anticipate any questions that they may in fact ask. Okay, so have a look at the flowchart. We'll give you a flowchart to a friend, get them to have a look at it, and then if there's something they don't understand, you can ask them, well, what would be the output of that routine? And if they can't tell you, then of course, then you ask them why, and then you put that additional detail in there. So you should be able to get to the point where you can give your flowchart to someone, they can actually run it in their head and be able to tell you what the output will be.